Okay, so it looks like we have a good number of people who have joined, so we might as well get started. So welcome everybody to the IR STIG webinar series. I'll start by introducing myself and give a few introductions, and then I'll introduce our speaker and we'll get going. So I am Meredith McGregor. I'm an assistant professor at the University of Colorado Boulder, and I'm one of the co-chairs of the IR STIG, along with Mike Semkoff, who's also on the call. For the webinar today, this runs like any normal Zoom meeting that you have been on recently, frequently in the last couple of years. So the speaker will give a presentation. We invite you to submit your questions as they come up through the chat window. So you can find the chat window by clicking at the bottom of your Zoom window and bringing it up. Please just type questions as you have them there. And then we'll have a full Q&A session at the end of the talk. We can ask questions out of the chat, and if you want to ask your question directly of the speaker, then you can use the raise hand function in Zoom to raise your hand, and then I'll unmute you and you can ask your question. If you have a hard time finding that, raise hand has been hidden under the reactions button in Zoom. So you go to the bottom of Zoom and there's something called reactions, and if you click on it, you can raise your hand. You can also use the chat window to report any technical difficulties. Hopefully we don't have any, and also submit any feedback, comments, or questions you might have for those of us on the IR STIG Leadership Council. We'll try and answer those if they come up at the end of the webinar, or we'll send you an email afterwards. And I think the only other thing to note is that we record these webinars and then we post them later on our YouTube site and link it through our webinar webpage. And I've put the link to that webpage in the chat window. Okay. I think that's everything that I need to do up front. So today we're very excited to have Dr. Joseph Masiero give us a talk. He's a scientist at Caltech IPAC working on the Surveyor mission. Joe is also the deputy PI of the NEOWISE mission, and his research focuses on the physical and dynamical properties of asteroids in the near Earth and main belt populations. And today his talk is going to be titled Hunting Asteroids in the Infrared, NEOWISE and Surveyor. And with that, I think I'll let Joe take it away.
Thank you very much, Meredith. It's a pleasure to be invited to give a talk to all of you about all the cool things that NEOWISE has been seeing and all the really cool stuff we expect the Surveyor to come up with too. So let's launch right in. Okay, great. So let's start with kind of an overview of what are asteroids and comets, and what do they tell us, and why are we bothering to hunt for them at all? And so this is a really great graphic that Emily Lakdawalla, who at the time was the Planetary Society, put together, showing the various asteroids that had been visited by spacecraft to scale, both in size and in reflectivity, in their color and how much light they reflect. And this is just, shows the variety of places we've been, but also the variety of compositions that we can see, things that, look like concrete, like Lutetia, whereas Matilda looks more like very dark asphalt or a lump of coal. And the comets in the bottom there, you can see Halley, Barali, Tempel 1. Those are all the comets that have been visited by spacecraft. They're all really dark surfaced. And these surface properties, both the shape of these objects, what they're made of, what the surface composition is, how reflective it is, and what kinds of light it reflects, all of this goes into what the objects are made of. And from that, we can infer what went on as the solar system was forming, how the various things were being assembled, how the planets were being assembled, the giant planets, the terrestrial planets, because the asteroids and comets really are the leftovers of formation. They're the things that weren't completely absorbed by everything else. And so they offer us this time capsule into what was happening right when our disk formed. Now, they've undergone a lot of processing, and a lot of the research that goes into understanding asteroids is how they have been processed over the last 4.5 billion years. And what about them has changed and what about them hasn't changed. And I'm getting the call on my office phone for the first time ever. Ever. So we have to figure out what's changed with them, but they do offer these snapshots of various phases of solar system evolution. And so this is what makes them so interesting to study, and the variety of them, and why we want to look at the population, both finding individuals and visiting individuals, but also getting a broader view of all of the asteroids. And so here I'm showing all the ones we visited. This was made before Hayabusa 2 and OSIRIS-REx visited their respective asteroids. Both of them would be about the size of each half of Boreal right here. So you'd expect two little dots about as dark as this. But this is the data we have from in situ. But if we look at all of the asteroids we know about, right now our current catalog contains over 1 million objects that we are tracking the orbits of, that we know where they are going around the sun, and some little bit about them. Sometimes it's not much more than an orbit. Sometimes we know the size and the albedo. For a smaller subset, we know we have spectral taxonomy. And so there's this gradation of data. But this is a top-down view of the solar system here. The cyan orbits are the planets, with Jupiter being the outermost ring here, the sun in the middle. And each of these dots represents the instantaneous position of an asteroid at the time this figure was made. Green dots are the objects in the main belt. That's the region of space between Mars and Jupiter that's roughly stable on the 4.5 billion year timescale. And so these objects are effectively unchanged. They've been kind of hanging out there for the majority of the lifetime of the solar system. The red dots are objects that come near the Earth's orbit. And so these are things that, due to dynamical or collisional events, have been left this stable main belt region and gone onto terrestrial planet crossing orbits. And I note that, if you see there's red dots all out here too, that's because a lot of them have very high eccentricities, very high ellipticities to their orbit. And so spend a lot of time far from the sun before whipping in, crossing the terrestrial planet zone. The blue squares here are all of the various Jupiter family comets we know about. And these little blue dots here are the Trojan asteroids trapped in a one-to-one resonance with Jupiter. And so each of these different populations, again, is a different snapshot from a different time and has a different evolutionary history, but all were drawn from the same forming protoplanetary disk. And so each offer a little glimpse of what was going on in a certain region at a certain time. Now, of course, the solar system, our knowledge of the solar system didn't always look like this. If we go back not that long ago, a couple hundred years ago, this is what we knew about the solar system. Right? We knew that there was Mercury, Venus, Earth, Mars, and Jupiter, and the sun, and that was about it. And shortly before this, a new planet was discovered, Uranus. And this opened up a new kind of search, a new way of looking for things that, hey, maybe there's more in the solar system than we had previously known about. And so people started looking in this kind of awkward gap between Mars and Jupiter for the quote unquote missing planet. And what happened was, shortly after the search began, it was found, and we found an object and we said, great, we found Ceres, we're good. Except about 20 years later, 4 more objects were found and the planet count went up to 12. And after another gap of a couple decades, more and more objects started to be found. Now, this is again before cameras, so all this is done by eye, but these objects are being found as part of these regular surveys of the sky. And sometimes they were, ad hoc and as people felt like it and when they could search, and they would only look in certain regions. And it wasn't really until the advent of CCD cameras being put on telescopes, photographic cameras then, that really increased the, someone have a question? No. Okay, really increased the rate of growth of our knowledge about this population. And in the 90s, it really picked up, giving us the population we know about today. And so this is, that same view of the solar system I showed before. You can't see the NEOs here because they're all really faint. There aren't that many of them. The main belt dominates the numbers of objects that we know about. But we are tracking all of these objects, and the surveys are continuing today. Now, one of these surveys that we used to both find and characterize objects was NEOWISE. And so NEOWISE right now is a PI-led mission by Amy Mainzer, who's at University of Arizona, under the Planetary Defense Office. And it utilizes the WISE spacecraft that was brought out of hibernation in 2013. We're using 2 simultaneous imagers at 3.4 and 4.6 microns, and we're passively cooled to around 75 Kelvin. We originally had cryogen on board when the spacecraft was launched. That we ran out of that about 7-8 months after our survey began. And we've been in passive cooling ever since, but we've been able to hold temperatures at around 75, 77 Kelvin, depending on the season and the time of year and the insolation. We're still in the same orbit WISE was in. We have no propulsion on board, no way of changing that. We're following the day-night terminator roughly, scanning outward, looking outward from the Earth, and just scanning the sky in rings around the sky. And over the course of 6 months, we build up a map of the entire sky. Over the year, we build up 2 maps. And what we do is, in the overlap regions between where these scans are taken, we look for things that move from visit to visit. And this is how we look for these moving objects, the asteroids that are moving with respect to the background stars. NEOWISE science operations started in December of 2013 and will be extended at least through June of 2023. We've been, as the surveys continued and as the spacecraft has continued not to have problems, we've received multiple extensions, with the latest extension running through June of 23. And the goals of our mission are to conduct this mid-infrared survey for near-Earth objects, both to discover new objects, but even more importantly, to get physical property characterization of these objects, because infrared light is incredibly powerful at helping you figure out how big an object is and then how reflective it is. Now, NEOWISE made use of the WISE spacecraft. And this is an infrared picture of the launch of the WISE spacecraft, an infrared telescope. So I really like that one a lot. Which WISE was a NASA mid-class explorer. The PI was Ned Wright at UCLA, and it was designed to be a 6-month survey of the entire sky at 4 wavelengths, 3.4 and 4.6, which were using Mercatels, and 12 and 22 microns, which were using silicon arsenic arrays that had to be significantly colder, only a few Kelvin above absolute zero. WISE is a 40-centimeter primary mirror and was cooled with solid hydrogen so that all of this, especially the long wavelengths, could function. We were launched in December 14th, 2009 onto the sun-synchronous orbit, and our survey ran from January 2010 to September of 2010. And over the course of the survey, we got at least 8 detections along any spot on the ecliptic, rising to hundreds of detections at the poles. And this was the main survey of the WISE mission. It was a 4-band all-sky survey with the goals to detect the most luminous galaxies in the universe, the coldest and closest brown dwarfs, and to be an infrared atlas for James Webb and other future surveys. And you can see here this infrared atlas that was compiled at the end of the survey, showing the 4-band full sky view with the galactic plane in the middle. The greens and the reds show you the longer wavelengths, the 12 and 22 micron, where you can see dust emission. The blues are all the stars. You can see the bulge pretty clearly right in the center of the galaxy. So it's a pretty fabulous image. But it shows that we met our goals, at least for this. But what's interesting about WISE is that nowhere on the original docket were asteroids, was any kind of science for asteroids. In fact, the original mission plan wasn't going to save the single frame data you would need to look for things that changed over time. And so NEOWISE started life as an add-on to the WISE mission that captured that single frame data, archived it, and did this search for asteroids. Because otherwise, the solar system objects and stationary transient sources would have been lost. All that would have come out of it was this total, was the Atlas catalog. And this is a really great image. I love this because you can see these chains of green dots are a coed that was made specifically to emphasize things that were moving over time. And so you can see this chain of asteroids moving across the background star here, and another chain of an asteroid that's showing a chain of detections moving in front of this nebulous feature here. So there's a lot going on in these data. It's really exciting. So what NEOWISE started out as was doing this search, right, with the WISE moving object processing system. And this was, a computer routine that searched for transient sources in the data, removed anything that wasn't moving, and then tried to link together these detections into trackings, into chains of detections that we think are associated with a single object. And this just shows an example image of what was presented to the human QAers, to the people who went through and checked whether or not, and in fact, still to this day, go through and check what the computer has found to see, is this a real source or is this a chain of noise points? And what we're showing is the W3 and the W4 and along the top, and then some background information about, the same RA deck at different times, the same pixel position at the image before to look for latent images. And just to confirm that these are in fact real detections. What's really nice is, of course, you can see the RA deck images are pretty blank. The sky was really empty at W3 and W4 wavelengths, which made the survey really incredible. And as I'll get to later, feeds into our decisions for why we choose the wavelengths we did for Surveyor. So over the course of the WISE survey, NEOWISE captured this data, did this search, and detected over 150,000 objects in our solar system. The majority of those are main belters shown in black points here, but you can see the comets marked in yellow and blue squares, and the near-Earth objects marked in red and green circles, with the red ones being ones that were discovered by our mission. And so over the course of the survey, right, we're sweeping out a chunk of the solar system, constantly taking pictures, reporting these to the Minor Planet Center, building up the orbits we needed to be able to find them again in the future. And so this was an incredibly successful survey. You can see we've detected over 400 near-Earth objects from this 7-month period alone, 150,000 main belt asteroids, dozens of comets, I think upward of 100 comets that were detected, many with 20 some odd discoveries. So it was really successful and showed the power of mid-wave infrared light being used to detect, discover, and characterize these objects. Now, when I say characterize, what we get from the infrared, and so I'm showing here spectral energy distributions for asteroids. So a near-Earth object on the left, a main belt asteroid on the right, for different reflectivities. And these vertical bars here are the 4 band passes that WISE used. So W1, W2, W3, and W4. And what you can see is that asteroids, most of their light is coming out at the wavelengths that WISE was especially sensitive to. The reflected component over here and the emitted component over here, the emission is significantly brighter. And so a 40-centimeter infrared telescope is comparably sensitive to a much larger ground-based optical telescope just because of this 2 order of magnitude change in Jansky flux between them. And WISE, of course, was limited because of the survey scan. We were limited to 7.7 second exposures or 8.8 second exposures in W3 and W4 for our detections. So these are really short with a 40-centimeter telescope, yet we're detecting things that are difficult for 2 or sometimes even 4-meter class optical telescopes to detect. And so, this is where the power of infrared is. But what we also do is we can constrain this curve here. And you can see that for a bunch of different reflectivities, while the visible light changes by an order of magnitude. And so here PV is the geometric albedo at V band, so ranging from 50% reflectivity down to 6% reflectivity. It doesn't change much in terms of emission. And so if you get an emission measurement here, and because you know the orbit of the object, you know the distance from the Earth to the object and from the sun to the object, really the only thing left to solve for is the diameter. And so you get a very strong constraint on diameter almost immediately just from a single snapshot at these wavelengths. And this is true all the way out to the outer main belt and even to where the objects, the Jupiter Trojan objects that are orbiting in the Lagrange points with Jupiter. Out beyond that, you can see that the Reen side of the distribution starts pushing into the W3 and W4. And so we get relatively less sensitive to things out beyond Jupiter. But for anything inside of that, these wavelengths were fabulous and were more powerful than most of the ground-based telescopes doing similar surveys. So by being able to fit diameters, and then if you have an optical measurement from effectively anything else, and you can propagate what the expected brightness should have been at the time NEOWISE observed it, you can measure that reflectivity. So on the SED here, all you need is a single visible light measurement, and you can figure out pretty quickly which albedo line this corresponds to, where this would fall. And so now you get a constraint on size and reflectivity as well as orbit. And so this is just a catalog effectively of what we found over the course of this cryogenic mission. Every point here is an asteroid that we measured with the semi-major axis of the orbit in astronomical units plotted here, the inclination, that is the tilt with respect to the plane of the solar system shown here. The size of the point is the diameter that we measured, and the color of the point is the reflectivity, where black is these cometary, very low albedo surfaces going up to reds and yellows for the highest albedo surfaces. And so what we can see right away, you can see the structure of the main belt, the Kirkwood gaps here that are caused by resonances of Jupiter, the transition where you have a lot more brighter stuff in the inner main belt, and it starts to fade away. And by the time you get out to the Hildas and then the Trojan asteroids, it's a significantly darker population with very little high albedo material. And this is tracing this gradient through the solar system of this compositional gradient that either is an actual gradient at this position, or what current research is indicating is it's possible that a lot of this dark stuff was implanted from out here, from out beyond Jupiter in the ice giant and gas giant region of the solar system. And as these planets were forming, a lot of this material may have actually been pushed inward here. So either you're showing a gradient in this zone or 2 different populations that were mixed as the planets were scattering around. If we look at this, a similar view just of the near-Earth objects, the near-Earth object population, because it's planet crossing, it's chaotic. And so it's a lot more mixed up, but you can start to see these kind of changes, right? You can see pretty clearly that these darkest objects over here, and again, this color bar is showing the albedo, the percent reflected light, the darkest objects tend to hang out in the farther areas, the distances farther from the sun. This cutoff here is artificial. It's the definition of what a near-Earth object is. It has to have a semi-major axis less than, a perihelion distance less than 1.3 AU. So this line here basically is showing that. But you can see that a lot of these dark things here are stuff that the eccentricity has been pumped up by planetary gravitational perturbations, and then they enter planet-crossing orbits. Whereas as you get to kind of the population on more circular orbits near the Earth, you're seeing a different compositional makeup. And this is actually tracing where in the main belt these things came from and how they got moved from the main belt population into the near-Earth population. So NEOWISE, after we ran out of cryogen, NEOWISE picked up the spacecraft and on a 4-month period continued the survey from the exhaustion of cryogen at the end of September in 2010 through to the beginning of February 2011 to basically close out the main belt and to do this final survey of this gap here, basically, where we ran out of cryogenic material, the cryogens on board. We could still sense objects. We lost about an order of magnitude sensitivity. But we were still good at finding near-Earth objects. And that was really the most important thing. So showing again this SED now with just our 2 short wavelengths after we lost cryogen, you can see that, for the main belt, we're not sensing this thermal emission curve a lot. There's this mixture of emission and reflection that makes interpreting the main belt thermal emission more difficult. But for the near-Earth objects, we still are sensitive to the emission curve. And that's what lets us get the diameter constraint. And so NEOWISE is still really good at finding near-Earth objects, even without the cryogen on board. And so that is what precipitated us to reactivate the spacecraft. So after February 2011, the spacecraft was put in hibernation, and it was in hibernation for about 2 3/4 years before NASA asked us to turn it back on and to see what it looked like and if we could still conduct our survey. And so in October of 2013, we turned it back on. It was in an orbit where it wasn't cooled. It was basically pointing at Earth half the time. And so the inside was pretty hot. So over the course of a couple months, we let it cool down to operating temperatures. And when we finally restarted the survey, we found that the data looked exactly the same. That the nearly 3 years of temperature of every orbit getting a fairly sharp temperature spike hadn't changed the detector properties significantly. And that's what said that we could, allowed us to continue our survey in this reactivation mode from December of 2013 to the present day. So what we've done is continued again to get these physical properties for near-Earth asteroids. And so from our first 7 years of survey, what I'm showing here is the diameter we've measured for near-Earth objects compared to this visible albedo. In cyan, these are the objects that were discovered by other surveys, and black are objects that we discovered as part of our survey. And so there's over 1,000 objects that are up, actually over nearly 2,000 objects on this plot right now. But what's really interesting is you can see that our discoveries tend to cluster in this lower area here. NEOWISE is really good at finding dark objects that are, in the 200 to 1 kilometer size range. That's an area that's being missed by the current ground-based surveys. You can see that there's a lot of smaller bright objects being found in the cyan points here that are missing over here. It's not that this population isn't there. It's that these are harder to detect because the low optical albedo means that it's really hard to see smaller things. They just don't reflect a lot of light, but they still emit it. And so this is, NEOWISE has been very successful at finding these objects down here and helping us fill out this population, including a few objects that are larger than a kilometer, which 1 kilometer is kind of the line we draw for, global hazard. In addition to what's being found automatically in the survey, NEOWISE is archiving all of our data. And so it lets us go back, take objects that are discovered by other surveys, and search our data to see if there might be a few detections of it. If for some reason our automated survey can't identify the object, maybe it wasn't seen enough times, maybe it was slightly too faint, or some other reason that it wasn't found, and search our data to see if we do have those detections, extract them, report them, and to get sizes and albedos for that. And so that's what I'm showing here. Black are the things that are automatically detected, and red are things that are manually found, manually recovered. And this has allowed us to get 500, 600 more asteroids that would otherwise not have physical property characterization simply by just looking in the data. So there's a lot of stuff hiding there. And again, there's a paucity of objects down here. That's not real. That's not that there are no objects down there. All these red points are things that are discovered by visible light surveys that we're searching for. So their biases, their detection biases are encoded in the population we can search for. So it just means that there's probably as many objects up here that should be down here that just we haven't looked for yet. So there's a lot of stuff hiding in this data. So I've talked a lot about near-Earth objects and getting their sizes and reflectivities, and that's great, but why do we care? Why are near-Earth objects in particular so important? I'd like to show this. This is a flyby image of the, actually it's an approach image of the near-Earth object Itokawa that was taken by the Hayabusa spacecraft, Hayabusa 1. And it just shows that like near-Earth asteroids, especially in this small size range, this couple 100-meter size range, are bizarre places. This is not a world like we think of that's a nice ball with things going on. This is a gravel pile where it's loosely held together. It's seen multiple generations of collision and gentle restructuring and collision. It's possible that this is actually, two lumpy objects that just are lightly touching together and some material has flowed between them, but they're two distinct cores. So there's a lot going on and they're weird and they pose a hazard to us, right? They're called near-Earth objects because they come near the Earth and occasionally they do hit us. And this is a map of all the fireballs, the bolides reported by US government sensors from 1988 to the present. And you can see that, there are small objects hitting us all the time. Most of these things are, 1 meter in size or less and just make a really bright meteor. Sometimes they explode, they have big flashes in the sky. Occasionally they're bad, right? This big red one here, that's the Chelyabinsk event that came in over a city in Russia and exploded, blowing out windows for thousands of buildings. But things are hitting us all the time. And so this is a screenshot of the Chelyabinsk event. And there's apparently rampant insurance fraud in Russia. And so everyone had dash cams. And so within a few minutes of this event happening, people were already uploading stuff to YouTube and there were dozens of videos and you could triangulate positions based on this. But you can see that, in the daytime sky, this giant fireball exploded. And we had no idea it was coming because it came from the direction of the sun. And it was only, the size of a house. It was 17 meters or so in size. It wasn't a huge object, but it still caused a significant amount of damage. So as you scale up, right, your impact energy goes as mass and velocity squared. And so mass goes as radius cubed. So if you get a little bit bigger, you start dumping a lot more energy into the impact. And so bigger objects can cause somewhat significant problems. And if you get very big to the multi-kilometer scale, of course, you get massive global impacts. And, I can't give an asteroid talk without talking about the fact that dinosaurs were wiped out by a killer asteroid. So here's the obligatory slide showing the Chelyabinsk event causing global panic and havoc. But while it happened 65 million years ago, there are still very large asteroids hanging around in planet-crossing orbits that we really should pay attention to. But NEOWISE, again, is looking for these hazardous asteroids, but there's a lot more that comes out of it. To date, there have been over 1,800 publications that have made use of the NEOWISE single frame data or the NEOWISE derived physical properties. And nearly, over 3,500 publications making use of all phases of WISE mission data. And you can see that the number of publications with time is growing. It hasn't really flattened out. And what we've seen from previous surveys like IRAS is that this continues to grow and stays at a high level for many, many years. And so this really is, a heritage archive, not just for asteroids, but for a range of solar system, galactic, and extragalactic science. So let me go over a few of the fun solar system results that we've gotten from the NEOWISE data. The main one was debiasing our survey. Because we were in a very well-known orbit where we didn't have weather issues, we didn't have spacecraft issues, we knew what the sensitivity was. It was constant over the life of the cryogenic mission. We were able to debias that survey and to run a sample population through a simulator, say what would have crossed into our field of view, what fraction of the objects would we have detected, and then use that to take the objects we did detect and infer what the real population of objects is. And all of this allowed us to set a number for how many near-Earth objects larger than a kilometer there are in our solar system. And we got 981 plus or minus 19 near-Earth objects. And these are of the global scale. But what's important is that over 90% of them are currently known. If you look at the cumulative count we have, we're up well over 900 now. We're in like 950. So there's a few being discovered every so often. But for the majority, we've reduced the risk of these objects simply by making sure we know where they are and we know that they're not hazardous. Because that was, one of the main goals of the mission. But we've been able to learn a lot about other aspects of the solar system as well. One of my favorite things is looking at the reflectivity, this albedo again, compared to what spectra have told us about their taxonomy, about the mineral makeup of the surface. And you can see the correlation here, especially if you look larger than a couple kilometers here in this region, this real tight correlation between albedo and spectral composition, where the S objects all tend to fall in here, the Bs, the Cs, the Ds all tend to fall in here. As you get to smaller sizes, you start seeing the optical selection effects, both of the discovery surveys and then the surveys that are taking the spectra of these objects, because you have to be both bright enough to find it and then bright enough at a second epoch for a spectrograph to take the data. And so there's a real strong selection against these dark objects. But you can see that this trend seems to continue down to relatively small sizes. As I showed before in that figure, and now I'm just showing in a histogram form, there's this gradient in reflectivity across the solar system where the near-Earth objects tend to be dominated about 2/3 to 1/3 bright objects to dark. When you get out to the main belt, it tends to be about 50-50, maybe a little bit in favor of these lower albedo objects. And when you get out to the Jupiter Trojan population, they're entirely in this low albedo complex. And so again, this is showing this gradient through the solar system that traces back to where these things formed and what they're made of. One of the other really powerful tools that when you have albedos is untangling confusing situations. So one of the things I like to look at are asteroid families. These are single objects that have undergone a collision, broken up into many smaller particles, and then those have evolved over the intervening millions or billions of years. And so how these objects break up, we can unwind that to figure out when the impact occurred. We can look at the various compositions of that thing, of the various family members, to get a better handle on what the composition of the pre-impact body was. And you can do this dynamically by linking orbits together, but there are confusing cases like this Nissa-Polana complex, which looked kind of like the thing took a right turn somewhere in here. But as soon as we took our albedo data and overlaid it on this, we could instantly see that what we were looking at is two very distinct compositions, two very distinct populations, this low albedo blue population and this high albedo orange population that just happened to be coincidentally overlapping in this three-dimensional space that we were searching for families. And so albedos allow us to separate these out and to do independent searches for these populations based on, so include effectively composition in our search space when we're looking for asteroid families, when we're looking to trace history of impacts in our solar system. And so we did this search using the NEOWISE data, pulling out all of the families and showing, so here I'm plotting just the families, their inclination against the major axis. So every asteroid associated with a family, and then all of the background objects. And you can see how this background population gets a lot smoother all of a sudden when you take out these clumps of asteroid families. Because with an asteroid family, one object breaks up and makes thousands of small pieces. And so they tend to dominate the local number statistics. So by removing them, now you're getting a look at what this background gradient was. And this is important because families represent over 1/3 of all known asteroids, possibly more. We were also, in addition to debiasing the near-Earth objects, our team also debiased the Trojan population. And so these are the objects in the leading and trailing clouds, the Lagrange 4 and Lagrange 5 clouds around Jupiter. And those clouds are stable over the age of the solar system. The things in there we believe were captured as Jupiter was forming and moving inward slightly and then frozen its orbit. It basically grabbed a snapshot of what the small bodies around it were at the time and froze them there. And so whether or not Jupiter grew or moved or how it moved is encoded in these two populations, and whether or not they have equal numbers, or if there's, or what the difference in population between the leading and trailing cloud is. And so by doing this debiasing here, we were able to get this dash line and show that, the leading cloud did in fact have nearly twice as many objects as the trailing cloud. And this sets constraints on how our solar system formed. The WISE W2 band in particular is located where cometary emissions in carbon dioxide and carbon monoxide emission lines are. And so by looking for excesses there, we were able to measure carbon dioxide and carbon monoxide emission excesses and thus production rates. And so this is work that James Bauer led, looking at this carbon dioxide production rate as a function of distance from the sun for two different kinds of comets, the short period and the long period. Now, the long period comets are things coming from the Oort cloud. We believe that they're brand new. They have only been in maybe once or twice before into the inner solar system. So they should be pristine, whereas these Jupiter family comets, the blue ones, have been going around the sun on shorter orbits, and so should be more baked, right? Shouldn't be quite as pristine. And yet we find that these two populations seem to show very similar behaviors with the CO2 production rate. CO2 is very highly volatile. And so you can see out here beyond 4 AU, it has basically a flat emission curve, but you're still producing this gas out to 8 AU or further. And then as soon as you get inside 4 AU, water starts getting emitted, starts volatilizing and kicking off additional CO2. And so you basically show this growth in CO2 production as any CO2 entrained in water ice starts to volatilize as well. But these two populations showing similar, two populations showing similar behavior seems to indicate that even though the Jupiter family comets have been around the block a lot, they're still dredging up pristine material just below the surface. And occasionally, when we do our survey, we find a really cool comet. And so C2020 F3 NEOWISE, some of you may have heard about, brightened sufficiently to become naked eye visible in the summer of 2020 and captured the interest of stargazers from around the world. And so I just grabbed a couple of the fun photos from APOD that I really liked of comet NEOWISE over various locations, including the one in the middle, which was taken by the astronauts on the ISS. But so this is one of the fun parts of doing asteroid surveys, is occasionally you find a really bright comet. So our data are public, and we have regular data releases. In fact, we have one coming up in a couple weeks, releasing the year 8 data. And you can access all this data on URSA, so the Infrared Science Archive at IPAC. The website down there is at the bottom. We have image data, we have catalog data available. And so all of this stuff is being made public because we want the community to use it to do all kinds of interesting science investigations. Again, spanning everything from the solar system to the most distant quasars. If you're interested in the derived diameters and albedos, these are hosted. There's a site on URSA. You can also get them from the Planetary Data System, which the link is down below there. And that will give you diameter, albedo information, and all the derived properties from our papers. So that's the end of the NEOWISE thing. And what NEOWISE has taught us is, there's a lot of information we can gather about asteroids and comets in the infrared, but also infrared is an incredibly powerful tool for finding these objects and characterizing the hazard to Earth. And so in light of that, our PI, Amy Meinzer, with our team, proposed the Near Earth Object Surveyor mission to NASA. And after a few iterations, as first it was really called NEOCAM, now we're called Near Earth Object Surveyor, but the design is effectively the same. And our goal is to make a 50-centimeter telescope with two 16-megapixel Mercator arrays, simultaneously imaging the same patch of sky, one at 4 to 5.4 microns and one at 6 to 10 microns. Now, what we saw with NEOWISE was that cryogens were our lifetime limitation. And so instead of putting it in a low Earth orbit, we want to move NEO Surveyor to the Earth L1. And so this puts it in a very calm environment where we don't have a lot of heat load from the Earth. And with this really massive sun shield here, we can passively cool the entire instrument down to 40 Kelvin. And that means we don't need to carry cryogen on board. We don't have any moving parts. And so we can basically extend the life of this mission by trying to design it to be very stable and to not really need anything moving or reduce the failure modes, basically. Over a 5-year survey, we anticipate that NEO Surveyor will detect around 300,000 NEOs. Currently, there's only 20,000 known, so that would increase our number of known near-Earth objects by over an order of magnitude, and over 8 million main belt asteroids. Again, there's only around 1 million of those known. So increase our knowledge of the main belt population by an order of magnitude. In addition to just detecting them, every object, because we have thermal infrared data, would get a size. And any object that has ground-based light measurements, possibly from LSST, sorry, Vera Rubin, possibly from another survey, we could get an albedo for. And so this really would provide a critical census of our inner solar system. Currently, Surveyor is under Phase B development under NASA's Planetary Defense Coordination Office. So some basics of Surveyor. Our goal is to detect 66% of the near-Earth asteroids larger than 140 meters within 5 years. 140 meters is a dividing line for where we think, from large regional damage down to stuff that's more localized and might be dealt with in a different manner. And over a 12-year extended survey, our aim is to detect 90% of the near-Earth objects larger than 140 meters. The reason that this kind of asymptotes off is because a lot of the last few objects are on long synodic periods. And so you really just have to wait until you cover them. There's not a lot you can do to speed that up. But 2/3 of them can be gotten within the first 5 years. In addition, we will detect a large number of objects in the 50 to 150 meter range. That will allow us to debias that population and constrain what the aggregate impact hazard to Earth is and how much we need to worry about that. So as I alluded to before, our bandpasses are chosen specifically to fall on the thermal emission portion of the near-Earth object SED. But also, if you look at here, the stellar source density as a function of wavelength compared to, basically how many bright stars are there how many stars are there brighter than your target asteroid? You can see that in the visible light, there are many more stars than your average asteroid. Whereas when you get down to like the 6 to 10 micron range, the sky empties out. And asteroids really are the brightest things in the sky. And so that makes detecting them a whole lot easier. Our detector technology, currently we're fabricating flight pathfinders and flight-like arrays for both the NC1 and NC2 channels. All are exceeding requirements. There's going to be 4 2K by 2K arrays mosaic together, and then a beam splitter there to allow us to look at the same area of sky with both of the 4x1 arrays. Over 90% of our pixels are meeting dark current specs. The long wavelength, the NC2 channel cutoffs are all out past 10.5 microns. And they're all shown to be operable up to 40 Kelvin, where we expect the passive cooling to be able to get us down to. So things are looking really good in the detector front. This is an image of one of the test detectors, and here's an image from the detector, because I know how important it is to actually have that part too. So yeah, we are getting live actionable detectors. One of the other things that NEO Surveyor is designed to do is to be able to scan a larger area of sky. So NEOWISE, because of the way it was designed, was really restricted to looking with only a few degrees of the tangent to the orbit of the Earth. Surveyor's viewing zone goes all the way down to 45 degrees from the sun out to 120. And the idea is just to march around the sky, doing one side of the sky and then doing the next side of the sky. And then 13 days later, repeating that process and continue this survey over and over to build up statistics on the detections of the objects so that we can fit orbits to those detections and complete our census. So here's a simulation of what that survey would look like over the first couple years. And you can see that as we march along the sky, every time we detect an object, we put it into our catalog and it becomes one of these green dots that we're tracking. And the initial detection of a new object is shown as the white dots. And so as we go around, we're continually finding new things as they move in or out of the field of view or get just a little bit closer to the telescope to come over our detection threshold. And so over the course of 5 years, we detect a large number of objects. And what's really impressive about this is that this simulation is only showing the largest near-Earth objects. I'm not showing the smaller ones, and we're not showing the order of magnitude more main belt asteroids that we'll detect out past the orbit of Mars. So there is going to be a ton of data coming out of this telescope. And when we run this simulation through and look at what our completeness is, again, the blue line here is showing Surveyor, orange is what we anticipate Vera Rubin to do with its LSST, and then yellow is going to be the combined set of these two telescopes. And it looks like that with our launch scheduled in 2026, that we will be able to cross that 90% mark when we add in what's currently known and being done with current surveys, what Ruben will do, what we will do. We should be able to cross that mark relatively easily with a high reliability. So, to conclude, NEOWISE really is providing a treasure trove of data on asteroids and comets, as well as stars and galaxies. And that near-Earth objects are really interesting because they trace this physical and dynamical history of the solar system and allow us to probe what was going on during planet formation. As I'm sure many of you are well aware, infrared surveys really allow us to provide a huge power by looking at things in a different way. And for asteroids, it lets us determine their physical properties for an unprecedented number of solar system objects. The albedo information we get is critical for understanding composition and family association and origin. And Surveyor will allow us to find over 90% of the potentially hazardous asteroids. And just to close, I want to say that, it's been my pleasure to work with Judy Pfeiffer for the last 10 years on the Surveyor, and before that, NeoCam. She was a lovely person, and I don't need to tell all of you how important she was to the field of infrared astronomy. All of the work I talked about is because of the groundwork and the foundation she laid. So we're really going to miss her. So yeah, with that, I'm happy to take questions. Thank you.
Wonderful. Thanks so much, Joe. That was really great. And thanks for the tribute to Judy at the end there. Okay. So with that, then we'll open this up for questions from everybody. So if you'd like to ask a question, and I see Mike has already raised his hand, then use the raise hand feature to raise your hand, and then I'll call on people and you can ask your question directly to Joe. So Mike, you want to go ahead?
Yeah, hi, Joe. I echo Meredith's recognition of your tribute to Judy Pfeiffer. This and many other things, including a good part of Spitzer, wouldn't have happened without her.
For sure.
Can you remind us, in terms of the potentially hazardous asteroids, it's a great talk, by the way, where are we now with NEOWISE, and where will we be with NEOSurveyor in terms of fraction detected?
So right now we're at about 25 to 30% of the potentially hazardous asteroids. NEOSurveyor, after 5 years, will boost that to conservatively 2/3, possibly more. Combined with Vera Rubin, and over the 10-year lifetime, we should cross 90% easily. So that's the mission is being designed with a goal of 12-year operations.
Okay, thank you very much.
You're welcome.
Okay, next up, Joseph Hora, do you want to go ahead? You can unmute yourself.
Hi, great talk, Joe. Just a couple questions I had. One is, what was the reason for choosing the short wavelength also to be on the thermal part of the SED? Because wouldn't you have been able to get your albedo information more easily if you had gone into something shorter than 4 microns, say? For
sure, yeah. If we had made that sensitive to half a micron, right, down in the visible, absolutely, we would be able to get albedos. But at that point, we're only a 50-centimeter telescope, and so we would not be sensitive to the vast majority of objects that we will be detecting at NC2.
Okay,
and
so you think most of it would be non-detections that would be useful. Okay.
Exactly. So instead, this is designed to basically, that's where the number of stars starts ramping up. And so to be an astrometric reference, it's really important to have that astrometric reference in NC1 so that we can map that to NC2. But also that's where we're going to sense this carbon dioxide and carbon monoxide emission from comets. And there are fewer comets, but there are some that are, have on these potentially hazardous orbits, and understanding how they emit both water and carbon dioxide will help us with, because their orbits can change on very short timescales. After one orbit of the sun, the next time they come around, the orbit can have changed because of this outgassing. And so part of it is to help constrain that as well.
All right, and just one other question. I was curious whether your survey strategy, do you think you would have detected the Chelyabinsk impactor?
So looking at our survey strategy, yeah, it looks like it would have been a low SNR, but most likely a detection about a month before impact, had Surveyor been up and running.
Great, thanks.
Yep.
We have a question in the chat, which is coming from an extragalactic background. And the question is, are there plans to do extragalactic science with the NEOSurveyor, such as finding luminous infrared galaxies and dusty quasars?
So right now, officially, no. We are funded by Planetary Defense, and so all of the main line and all of the design is for asteroid sensitivity. But you know, the data will be incredibly useful for a range of science topics and are going to be publicly released. And so there will be opportunities, and I've heard rumblings about, you know, what could be done if there's, you know, to flip the coin around and now to have astrophysics have an add-on to Surveyor that makes use of the data for, you know, galactic and extragalactic. You know, there's a lot of interest in that for sure, and the data will be there. So I hope that people do fun extragalactic stuff with it.
Okay. More questions from the audience. Stephen, go ahead.
Yeah, I was curious. I guess when you're assessing, you know, damage potential, you have to make assumptions about the density. So what are those assumptions? And is there any way to get a better handle on the density of these objects?
That is really, density is really interesting, right? I mean, we know we have iron meteorites that have densities of, you know, 8 grams per cubic centimeter. Most of the bigger things look to have densities, you know, comets look to have densities in the 1 or, you know, 0.8 grams per cubic centimeter. So even less than water, but a lot of that is driven by internal macroporosity, right? If there's boulders that are just sitting on each other, your bulk density is going to be lower. And so there's kind of this range of densities. However, it really only varies, except for the irons. Most of the stuff is somewhere around 2, you know, from 1 to 3 grams per cubic centimeter. So while that is a factor of 2 in mass, getting the diameter right matters more first. Once you have that, density will help you with impact energy, but I think even more importantly, it will help you with what will happen when it hits the atmosphere. Will it punch through or will it fragment and air burst? And those are 2 very different consequences that colleagues of ours at Los Alamos study for very different reasons. But you know, the different kinds of damage you get from different kinds of impactors that's where I think the density plays the biggest role.
I mean, can you infer some things, say, based on, you know, how shiny they are, or do they have more metal content or something like that?
There seems to be, you know, so these low albedo objects look like they had at some point in their history a significant amount of water in them. And that's now wrapped up in the silicates. It's not as ice, but it was, you know, mixed in with the minerals. And because of that, they tend to be crushy and porous. So there does seem to be a correlation with albedo and density, but it's weak. It's not a definite one-to-one. And I mean, as I showed you with Itokawa, right, that's a silicate object that you would expect has, you know, 3 grams per cubic centimeter rocks, but they're clearly just, you know, a gravel pile with boulders sitting on each other. So what the bulk density of the object is different from what the density of the, you know, clumps is, right? Yeah.
Thanks.
Okay, more questions for Joe.
This
Give
is Casey.
everybody a moment to think. Oh yeah, go ahead, Casey.
So Joe, you probably know what I'm going to say. I just want to mention that SphereX is a mission that is being built on the astrophysics side of the fence. It's going to be a 0.7 to 5 micron all sky survey that's going to have about 100 spectral bands. So if you will, low resolution spectroscopy around between 50 and about 150. And it should be like LSST, it's going to do an unbiased search in the sky. It's going to have about WISE sensitivity. So I'm really looking forward to seeing LSST and SphereX and NEO-Surveyor data all together on all these objects.
Yeah, no, absolutely. All of these combined, it's looking like it's going to be the future for planetary surveys and asteroid and comet surveys is looking really bright.
Yeah. And so I'm thinking that we're going to get good spectrophotometry, and we're going to be able to actually do your albedo measurements and also get you silicate absorption features and, you know, and maybe some interesting C-type asteroid features as well. So yeah.
Yeah, that'd be real cool.
And SphereX, I should say, is going to launch early 25 now. So when NEO-Surveyor, do you have a timeline for it? If you had to make your best guess.
Currently, our schedule is early first quarter 26, I think like March-ish timeframe, but that's what the design launch date is. Yeah.
So LSST will be on the sky first before either of those missions, but there'll be some good overlap. That's great.
Yeah.
Thank you.
Okay. More questions? We're always open for more questions. I'll make a few announcements while I give people a chance to think. want to thank everybody for joining us today. We usually have these talks on the first Tuesday of every month, so you can come find us at April, first Tuesday of the month at 1 p.m. Eastern time, and we'll have another IR STIG webinar. And I have to also put a plug in for our workshop that the IR STIG is organizing at the end of March. So I'll put a link in the chat for the registration page for that, but we're having an IR STIG workshop in Boulder, Colorado from March 30th through April 2nd to discuss the kind of state of IR astrophysics following the decadal survey. So we'll have, discussion about decadal probe concepts, looking forward to the future, science and technology drivers. And our registration deadline to submit an abstract is coming up on Friday. So if you are interested, please do register. The conference is completely free. And we really hope to get as much community participation as possible so that we can really kind of think about the exciting things happening in IR science. Okay, I don't see any other raised hands. So with that, let's all thank Joe again for a really excellent talk. I'll do the awkward Zoom clap for you, Joe. And then we hope to see all of you at future IR STIG webinars, talks, workshops, events. So thanks for joining.
Thanks all.
Thank you.